We're given two functions who were given intersection points of 0, 2 and 2, 4. This is f of x and g of x. And we'll be asked to find the area between these curves. We'll be asked to find a volume based on these 2D curves. And so I've included the related information for those calculations here off to the right in blue. I've also gone ahead and entered as y1 the function f of x and as y2 the function g of x. And simply because it's very typical that we need to calculate the difference between the two functions, I've identified y3 as f minus g. For a window, just to see which function is f and which function is g, I've chosen 0 to 2 given the domain, and ordinarily I'd go 0 to 4 for y min, but you'll see in a moment why I chose to go just a little bit below that axis. So when we graph these, what we have in blue is the f of x function. What we have in red is the g of x function, and in black we have the difference between the two. Keeping in mind that when the black function crosses the x-axis, that's simply identifying the point of intersection of the curves. So with that as our background information, let's go ahead and look at the problems. Again, this is the f of x curve. This is the g of x curve. So in part A, we're finding the areas of the regions R and S. Ordinarily, we might have to treat those separately. First calculating R, which would require the calculation of the point of intersection of the two curves, and then adding to it the area of S, being careful to keep the larger function minus the lesser function in our integral. But in fact, there's a simpler way to do that, and that's simply to use the absolute value in the integrand, so that in finding the area of R plus S, we simply need to subtract f of x minus g of x, because whether f is greater than g or vice versa, and worrying about when that transformation takes place, becomes unnecessary when we include the absolute value inside the integrand. So we can just go from 0 to 2. Let's see what we get when we calculate that. So we just need the integral from 0 up to 2. Remember, what I defined to be y3 was the difference of f and x. Oh, I need the absolute value there. Good catch. Absolute value, remember, is easy to find because it's just the first function in the catalog. Let's go back and get that y3. And we're going to integrate with respect to x. It's going to take just a moment to do that calculation, but the result we get 2.0043. Is the combined area of R and S. Part B asks us to find the volume that's created from the curves f and g. In general, volume functions are calculated by integrating the area as a function of x with respect to x, where the dx plays the role of thickness. But it's very important that we can visualize these what it is they're asking us to construct, so that we know with respect to which variable, whether x or y in any given case, we're supposed to be integrating. The key is the fact that the cross sections are squares perpendicular to the x-axis. So perpendicular to the x-axis means that we're looking at something like this. What are we looking at? We're looking at squares. Come out like this. Something like that. That means that we're also, because we're working just with region S, we are now going to have to find that intersection point that we avoided having to calculate in part A. So let's take care of finding the intersection point first. So we're going to find the point of intersection. Actually, strictly speaking, we're just going to find the x value of that intersection. And that is equal to where f and g meet. So let's go back to the calculator and recall that we programmed in y3 as the difference between f and g. And so all we have to do is calculate where that y3 function is a 0. There's our graph. What we want is this third function. And we'll choose that as a left bound. That as our right bound. We'll make our right bound the same as our guess. And there we have the 0. That's the point of intersection, or rather the x value of the point of intersection. 1.0328. We're going to define that as A and say that's approximately equal to 1.0328. But we'll actually use the exact value in our calculations, and we do that, of course, by saving the result that we got in A. Okay, so what are we doing? We're trying to integrate from that intersection point up to 2. But we're getting a little ahead of ourselves. Let's come back to our visualization. A key to the orientation and knowing how to write the integral is to ask ourselves what the thickness of these cross sections is. Clearly, in this case, it's dx. And that orients us to how to write our integral. Namely, we're doing an integral with respect to dx. That's far more common, but they could have asked us to handle cross sections perpendicular to the y, in which case we would have had to do the integral with respect to y. But now that we see the thickness is dx, and so we know that that's what we're integrating with respect to. We're going to go from a up to 2. And we just have to find out what the area of a square is. Well, it's the side squared. Now, what's the length of the side? Well, again, from this diagram, the length of that side is f of x minus g of x. We could, in fact, have gotten it backwards, namely g of x minus f of x, and still gotten the same result, simply because in this case we're squaring it. But in general, it pays to do the diagram, visualize just what it is that you're working with, understand what the thickness of your cross section is to tell you what you're integrating with respect to, and then get the area calculation correct. All right, let's find out what that is approximately using the calculator. So we're finding an integral. And we're going from our stored value of a up to 2. The function itself is going to be, again, that difference of f and g, which we have already entered as y3. We have to square that. And we're integrating with respect to x. Oops. .2831. Okay, what does part C ask us to do? We're defining h as the vertical distance between f and g. Okay, so realize that h of x is the very thing that we've already defined in the calculator to be y3. Now they simply want us to find dh dx at x equals 1.8. So again, go back into the calculator. We'll use the numerical derivative with respect to x. And we're doing that at x equals 1.8. Negative 3.8117.